Thank you. So thank you for the introduction, and I would like to thank the organizers of this seminar for giving me the opportunity to give a talk today, and of course the organizers of the SEMRACs for giving us the opportunity to work on these very nice projects. So indeed, I'm going to talk about some mean field control problems with congestion effect, and this is a joint work with Evacuation. So first of all, I will define mean field control in a very general way, and I will compare it with mean field games so that if you know mean field games, you will not be confused with what we're going to do in the next sections. And after that, I will present mostly two classes of models. So a first class, which is local, and a second class that is non-local. So I'm going to explain what this means. Actually, the second one was done earlier, but I feel that it's simpler to present the framework in the local model, so I will start with this one. And then I will briefly conclude. So for each model, I will give some results of existence and uniqueness, and I will show some numerical results based on two different methods. So let me start with the definition of mean field control in a very general way. So what we call mean field control, or control of MacKean-Vlasov dynamics, is defined as follows. We want to minimize some function j of a control v. So in other words, we want to find an optimal control v hat such that j of v hat is smaller than j of v for any v. So this is just a control problem, and the functional that we are going to consider, j, is the expectation of the integral between 0 and some finite time horizon, capital T, of a running cost, that I will denote L by L, and final cost, that I will denote by H. And note that the running cost and the final cost may depend on the position of some random variable, capital X, controlled by V. So I'm going to define the dynamics of capital X, sorry. And it also depends on this term in red, which is the distribution of x at time t. So I denoted this dependence with brackets because it might be non-local. So L and H may depend on the distribution of x at any point, right? So it could be a moment or it could be something more complicated. And the dynamics of x is given by MacKean-Vlasov equations controlled by V. So here the drift again depends on the position, on the control, and also on the density of x at time t. And the initial distribution m0 is given. And for the noise, here the volatility sigma is constant, but it could be also something that depends on the same parameters. But for simplicity, I will keep it constant in this talk. So let's try to compare mean field games and mean field control in case you are familiar with mean field games. So to do that, I rewrite mean field control in a slightly more general framework with functional j tilde, which is now a function of v and some distribution mu. And actually not a distribution, but a flow of distribution, right? For each time, I have one distribution mu t. So it's exactly the same thing as in the previous slide, except that now I fix the distribution in the brackets to be mu at time t. Right? So it is a parameter of the problem somehow. So to recover mean field control, I just have to prescribe the fact that instead of mu, I will take the distribution of x. Right? So this term in red will be the distribution of x controlled by v hat for the left-hand side or controlled by v for the right-hand side. So it's somehow a fake parameter because we don't really need it. Once I fix the control, I have the distribution of x controlled by v. Because in the dynamics, I also plug this distribution. So it's really a MacKean-Vlasov dynamics. Now for the mean field game, it's slightly different. When you want to solve a mean field game, you want to find a couple, v hat and mu, such that for this fixed mu, v hat is optimal. right? This is the inequality. And then we have two things. The first point is that X should satisfy a dynamics, which is now not a MacKean-Vlasov dynamics. Strictly speaking, it's a dynamics where I plug in the drift the distribution mu, which is prescribed by the problem. But I also require, this is the second point, that mu should coincide with the distribution of X controlled by V and parameterized by mu. So it may seem that we're doing the same thing, but actually it's different. So the first one, the mean field control problem, is really a control problem, whereas the second one is a fixed point with a control problem. And it turns out that in some cases, these are very similar, but in some cases are different. So I'm going to show one example at the end of the talk, but apart from that, you can almost forget mean field games for this talk. Just to conclude this introduction, these two problems, as I said, are different, but it's not really that one is better than the other, it's just that they model different things. So some typical motivations, for example, could be for mean field control, at least two motivations. One is that we are looking for a cooperative equilibrium or cooperative optimum, where we have an infinite number of agents, and all of them are using the same control. So you have, let's say, a global planner that gives to everyone some control, and then everyone uses this control. So this could be useful, for instance, in distributed robotics, if you want to plan the behavior of your robots. And another point of view is that you have a single agent with the dynamics that I've given before, the dx, and the dynamics and also the cost depend on the distribution of this single player. And this could be useful in risk management because you might have some criterion that depends on your variance or some other moments, so non-linear in the distribution. Now, for the mean field game problem, it's different. We have in mind a Nash equilibrium with an infinite number of players. So because there is this fixed point argument, which is really the limit when the number of players tend to infinity, of a Nash equilibrium for a finite number of players. So you fix the behavior of everyone, and then you try to find your optimal control. But then everyone does the same, so there is a fixed point, right? And here this is the same thing, but in infinite dimension, because we have distribution, let's say a continuous, for example, a continuum of player. And this could be useful in economics or sociology. So in this talk, as I said, you can forget mean field games. We are going to focus on mean field control. I will present two models, or two classes of models for congestion effect, and give existence and uniqueness results, provide some numerical results, and I will focus on the PDE system and the control problem. I will not talk about the stochastic analysis side, but for this I refer to the recent book of Carmona and Delarue and papers of these authors, and also papers of many other authors. So, first model of congestion. So the model is as follows. Let's say you have an infinity of undistinguishable agents on the torus in dimension D, so with periodic boundary condition for simplicity. And here nu will be a positive parameter, although in some parts of this talk it could be a degenerate diffusion. But for the sake of clarity here, I will take just a positive parameter. So the SDE for X is as before, except that now I take a very simple drift. The drift is simply V, so the control. And so basically it means that the agents control their speed. And that's it. And note that the control is of feedback form, so it is a function of X, which means that the agent at position X just looks at his position and then he knows what to do. He will do speed equals V of X. And again, here I'm writing directly the limit equation when you have an infinity of agents. But you could start with a finite number of agents, all using the same feedback, V, and then let the number of players or agents tend to infinity, and you would end with this equation. So here I refer to some recent work of Daniel Leiker to do that in a precise sense. So anyway, once you have this SDE, you can write, at least formally, the PDE satisfied by the associated distribution. So M superscript V. So it satisfies this Fokker-Planck equation. with some initial distribution m0 given. And in the divergence here we have m times v, because v is exactly the vector speed, the speed that you should use. Now the goal is to minimize j of v as before, but now here I will take for L a function of m, but in a local sense. So in other words, L depends on m only through m at position x, right? So I don't denote it with bracket because now it's not a function of the whole density, it's only a function of m at position x, right? So the agent will pay a cost that depends on his position, the density at his position, and his control. And there is a final cost, and here I take something slightly simpler than in the previous slides. ut is a function of the position at time t, and that's it, not the whole distribution at time t, just for simplicity. Now, this first line would go with the SDE, right? It's a stochastic control problem, but I can rewrite it as a deterministic control problem. So this is the second line, and I expand the expectation as an integral against the density, because x here is a random variable, but I know that the density of x is denoted by m superscript t, together with the Fokker-Planck equation. So now it's a problem of optimal control of Fokker-Planck equation, purely deterministic, and I'm going to focus on this aspect. So it has been shown in the book of Ben-Soussan, Fraise, and Yam that if there exists smooth feedback, v hat, optimal in the sense that it realizes the minimum of j, then v hat has to be of the following form. It has to be the gradient of h, with respect to the third variable, so here du, and dph should be taken at m and du. So when I write this, h is the Hamiltonian associated to the running cost by convex duality. So this is a parameter of the problem. Somehow if you have L, you know your Hamiltonian. Now what is not known is m and du, so I should specify what these objects are. So it's not a surprise, m will satisfy the Fokker-Planck equation as before, except that I replace v in the divergence by its expression in terms of Hamiltonian. And u satisfies some AJB equation, which involves the Hamiltonian, but also the derivative of the Hamiltonian with respect to m. The term in red in the AJB equation. However, note that here, since L has a local dependence on m, h also has a local dependence on m, which means that h depends on m at time t and position x. So actually, m in this equation is just a real number, so this dmh is nothing fancy, it's just a derivative with respect to a real number. Also, this term in red disappears in the mean field game. So if you know mean field games, you can do the same things. You can derive a Fokker-Planck and an AJB equation. They will be very similar, but this term in red will not be here in the AJB equation. So this is a system of forward-backward coupled PDEs, because the Fokker-Planck equation is forward in time with m0 given, and the AJB equation is backward in time with u at time t given by the final cost. Now let's move on to congestion. Yes? So u is the value function of the problem. It's yes, of this problem, but it's not exactly the value function, because if we go back to so yes, thank you. That's a good question. If we go back to, let's say, okay, the first slide, this one, you see that here j of v actually depends on the initial distribution that we choose. So, well, as you know, if you write the dynamic programming principle, you will get it on a value function that will depend on the control and the initial distribution. So it will be a value function on the space of distributions. So strictly speaking, if you do dynamic programming principle on this optimal control problem, you get the master equation, or something similar to the master equation on the space of distributions. But now if you specify it in some way, you get this AJB equation. So this AJB is not really the AJB associated to this problem, strictly speaking, but it derives from this problem. Or in other words, if you like, the AJB equation of this problem will be posed on the space of probability distributions. But once you fix the probability distribution to be m following the Fokker-Planck equation, you have a function of variable x only, because it is coupled with the right distribution, let's say. So you don't need to solve the problem on the whole space of distributions. So congestion. Actually, the model I'm going to present takes into account two effects that are different. The first one, the main one, is congestion. So by congestion, I mean that agents do not want to move in a very crowded region. So if you have a lot of people around you, you don't want to move because it's very costly. You have to make a lot of effort. So there are at least two ways to do that. One is to impose a hard density constraint. So you impose that the density cannot exceed a certain threshold, so some constant, which means if the number of people is already at its maximum in this region, then you cannot enter the region. But what I'm going to do now is rather a soft way to take into account congestion, which is we don't impose a hard constraint, so there is no fixed maximum for the density, but the agents are going to pay a high price when they move in a region where there are a lot of people. So the price, the running cost they are going to pay will depend on the speed they have and the number of people around them. And there is another effect, which is aversion, and this means that you do not want to be in a crowded region, even if you are not moving. So let's see how to do that. So I will consider the following Hamiltonian, h, as a function of x, which is in the torus in dimension d. M, again, is just a real number, positive, because it will be density at time t in position x. And p will be somehow the gradient of u. So the Hamiltonian is of the form some power of p over some power of m plus some L that depends only on m. So stated like this, maybe it's not very clear what this means, but let's take a look at the associated Lagrangian, so the running cost. So we do the duality, we derive some expression, explicit expression for the Lagrangian. It doesn't look very nice because we started from the Hamiltonian, because this is what is going to appear in the PDE system. So I start with the Hamiltonian. But actually you could start with the Lagrangian of this form and then derive the associated Hamiltonian. Anyway, this Lagrangian looks like a power of m times the power of psi, and think about psi as the control, v. So in other words, you see that this term in red means that if you are moving, psi will be positive, and then it will be multiplied by m. So if m is very large, you are going to pay a higher price than if m is small when you try to move. Fix psi to some value, so in other words, v to some value, and then depending on m, you will pay a high price or just a small price. So it's more interesting to move in regions where m is small, because this term in red will be smaller. Now you see that the term in L of x and m, may encode two things. So it doesn't depend on your speed, but it will encode a special preference. So for instance, you prefer to be at this x rather than this x. And also it will encode aversion. So think about L as an increasing function in m. Right? So even if you don't move, even if psi is 0, you are still going to pay L. Right? So you don't want to stay in a region where there is a high density. And now there will be a trade-off between these two effects, or these two parameters. Actually, there are three parameters, alpha, beta, and L. So let's take some extreme cases just to have some intuition. I'll recall the notation first, and then take special case 1. So beta is equal to 2, so beta star, which is the conjugate, is also 2, and alpha is 0. So in this case, you can write the Hamiltonian, you can write the Lagrangian, and you have a Lagrangian of the form psi square plus L. So it means that here there is no congestion, right? You pay your price depending on your speed, it's quadratic in your speed, but it doesn't depend on how many people are around you. Whereas if you take alpha equal to 1, Then in this case, it depends a lot on the number of people around you, because you have m times xi squared. So now that you are familiar with this model, we can play a little bit. So the numerical simulations that I'm going to show are actually realized using the method that I'm going to present later on, but it's just for the purpose of illustration. So let's start with the initial distribution, which looks like this. So it means here your domain is a torus between negative 0.5 and 0.5. So the two dimensions here are space, and this value here is the value of the density. Yeah, so it's uniform on some square inside the domain. On the right, you have the value function at the final time, ut. So you see that this value function is also uniform and positive inside the same domain. So in other words, if you stay there at the end, you are going to pay this price, so 1, whereas if you stay outside, you are not going to pay anything. So of course, it's, at the final time, you should be outside this domain, because you don't want to pay this price. So let's see what happens. Here I want to illustrate the impact of little l, so the cost of aversion. So I start with a quite small little l, so linear in m, let's say, with a small coefficient, 0.01. So here is what happens. Now it's only the density and the evolution of the density in time. So you see that indeed agents evacuate the square in the center. And at the end, you have a high concentration here around the boundary of the square because people don't have much incentive to go very far. They just don't want to be inside. But if the cost of aversion is not very high, like this, then it's okay. Even if they are in a crowded region, it's okay. Now, if we take a larger L, what do you expect? Yes, it will be more uniform. So actually, it even becomes completely uniform at some point. There is a transition, and then everyone remembers that they should exit the square before the final time. So they do it. But you see that we get something much more uniform. Now the impact of alpha. So I start with a distribution that is split into two parts, each of mass half. One is a very peaky hump, and one is a very small hump, but they have the same mass, 1/2. And they are attracted towards the center because of this final cost u. Right? So you will pay a small cost if you are around the middle of the domain, and a higher cost if you are far from the middle, far from the center. So the evolution will be like this. And note that here I rescale the vertical axis because otherwise we don't see much. So after a short time, you see that the two humps are more or less of the same size. Right? They look pretty similar and they are moving toward the center. Another remark is that here they do use periodic conditions because you see that there is some mass on the left side here, which comes from the other side actually, because this is the shortest path to avoid the crowded region precisely. Okay, and then the mass converge towards the center. And at the end, you see that we have something very peaky, but we don't have a Dirac because there is still the cost of congestion and aversion. So this was for alpha equals 0.01. Now if we take a larger alpha, what do you expect? So remember, alpha is the exponent of m. So if you have a higher alpha, you should have more congestion effect. And this means that now you have something like this. So if I stop around, let's say, time equals 1/2, you see that the hump on the left-hand side, the left side, remains higher for a long time. And this is because agents at the center of this hump are very they feel congestion a lot. So basically they cannot diffuse somehow as before. So before it was cheap to escape from congestion, but now it's not possible because if you are in a congested region, you cannot escape. You have to just stay there until the agents in front of you have moved or around you. Okay, and at the end we have something similar to the previous case. So for this model, so I recall here the notation for the Hamiltonian, and note that this Hamiltonian is not well defined when m is 0, right? And this will be the main difficulty of this problem somehow. So you see that in the PDEs I write h, but h is not defined when m is equal to 0, but you have seen in the numerical simulation that in some regions, some even open portion of the domain, m is 0. So how does that work? Well, so to do that, we have to introduce a notion of weak solutions. And we can show existence and uniqueness for this kind of solutions. And the way we do that is we need some estimates on the solution. So we say that phi and m is a weak solution to the PDE system, provided you have some estimates. But the main point is that the AJB equation on phi here, because phi is not exactly u, is satisfied in the sense of distributions and only with an inequality. Then the Fokker-Planck equation is satisfied with an equality in the sense of distributions. And we also need some technical assumptions, and this identity hold in red here. So it's a bit technical, but stay with me. There are just a few technical slides in this talk. So now, why do we introduce this kind of solutions? It's not obvious why this is the right notion of weak solutions. Actually, this approach is similar to an approach that has been used in mean-field games. So actually, this goes back to the first papers of Lazary and Lyons, and then Cardaliaguet, Graber, Porretta, Tonon, and others, where in these papers, the authors use the variational structure of the problem. So basically, I think that this approach worked because the mean-field game had a variational structure, which is not true in general. But for mean-field control, it's true in general because we always have a control problem. So in general, it will have a variational structure. Now, this relies on the natural interpretation of the PDE system as the optimality condition of some optimization problem on a Fokker-Planck equation. So the problem I've written before. And to this problem, we can associate a dual problem using Fenchel-Rocafella theorem. And then we introduce this kind of weak solution because it is compatible with these optimization problems in the sense that you have a correspondence. If I give you a weak solution to the PDE system, you can derive a couple solution to the primal and the dual problem, or rather a relaxed version of the dual problem, and vice versa. If I give you a solution to each problem, you can derive a weak solution. And also this notion of weak solutions allows m equals 0 in some regions. And we need that in order to have this Hamiltonian in the system. So I'm not going to do the proof, but I'm just going to write the two optimization problems because it will be needed in order to present the numerical method. So the first problem is similar to the problem I've started with. So if you look at the definition of B, it's basically the running cost plus the final cost. And there is a constraint that M and Z should be in the space K1, which basically says that M satisfies the Fokker-Planck equation, except that it's a linearized version because we made a change of variables. So here Z replaces M times V in order to have a linear equation. And we have to take that into account in the definition of L tilde. So L tilde is basically M times L, except that we have this change of variable. So V is equal to Z over M. And then this cost is L tilde is exactly what we expect, provided everything is well defined. Now, if F, M, and Z are both 0, we just put 0 for the cost, but in other cases, we will put plus infinity. Because we want to avoid that. We want to forbid that. And then, since we try to minimize, L tilde should not be equal to positive infinity. So this cost is convex, which allows us to do convex duality. So we can derive the dual problem, which can be written as follows. So it will be a sup over phi, which plays the role of u somehow, of a phi. And a phi is the infimum over m of a phi m, with a phi m defined like this. on the fourth line. And you see that basically it's the integral of what appears in the AJB equation, except that we don't have the derivative with respect to m of h. We can rewrite a of phi in different ways, and in particular this term in purple, which I'm going to use for the numerical method. So it is an infimum over phi of the sum of two functions, one capital G that depends on lambda phi, which is the derivative of phi, basically, plus a term that depends on phi only. So the numerical scheme relies on Augmented Lagrangian. So to write the Augmented Lagrangian, I start from the problem in the previous slide, so this term in purple, and I'm going to introduce a fake variable somehow. So because it's not very convenient to do this minimization like this. So I introduce a variable q that is required to be equal to lambda phi. And then I write that I should minimize f of phi plus g of q. So far I've done nothing. I've just introduced a fake variable somehow. But now I can write the Lagrangian associated to this optimization problem under constraint. So it's not the Lagrangian of the optimal control problem before, it is the Lagrangian of this problem under constraint. And I must find a saddle point of this Lagrangian, where sigma is the Lagrange multiplier. So this is equivalent to finding a saddle point for the augmented Lagrangian, which is the Lagrangian plus some penalization term, which penalizes this constraint. So q minus lambda phi with some parameter r. So think about r as maybe 1, just 1. So now these two problems are equivalent. Finding a saddle point for the first one is equivalent to finding a saddle point for the second one. So the reason why we introduce the augmented Lagrangian is because it will somehow fasten the numerical convergence. Now, here is the first thing we could do with this augmented Lagrangian. We want to find a saddle point. So one way to do that is to minimize with respect to phi and q, the augmented Lagrangian, and then update sigma using some gradient step. So here we start with some initial phi 0, q 0, sigma 0, and then we construct iteratively some estimates, some approximation of the solution. And the way we do that is first we minimize our phi and q, and then we do a gradient step in sigma. So it can be shown that this will converge towards a solution of the problem, so a saddle point. But actually we can do something slightly smarter. So we can decouple the problem in phi and q. So this is called alternating direction method of multipliers. And the idea is that first we fix, let's say, q from the previous iteration. And we minimize in phi. So you see that this is a simpler problem than before, because we have just one variable and also some terms just disappear because we are minimizing with respect to phi only. Then we do the same thing for q. We fix phi that we have just computed and we update q. And then we update sigma by the same step as before. Right? So we split a single minimization in two variables into two minimizations. So the first step actually amounts to solve a finite difference equation on phi if you write the optimality condition. The second step amounts to calculating some proximal operator. So this is non-trivial in general, but for the congestion model I've presented, we can do it almost explicitly. We have just equation to solve a root of a polynomial, in dimension 1 to find, so it's not too hard. And the last step is very straightforward. So for the numerical implementation that I've shown before, and that I will show now, we take nu is equal to 0, because if you don't do that, then in the finite difference equations that phi has to solve, because of the first step, you will have some B Laplacian, and then it seems that it's harder to solve numerically, so we need some method to do that more efficiently. But if you take nu equals to 0, the matrices are sparser, so it's easier to solve. Now, just to conclude on this section, I would like to present a model, a case where we take into account some other boundary conditions, because periodic boundary condition is not very realistic. So to do that, at least numerically, what we can do is we take, let's say, the square, but we define the Hamiltonian in different ways inside the domain and on the boundary. And on the boundary of the domain, we require that the speed should point towards the inside of the domain, the interior of the domain. Once you have defined your Hamiltonian like this, you can derive the Lagrangian by duality, and you can redo the same thing as before. So this tells you that when you are on the boundary, you cannot take a speed that would let you go outside of the domain. Of course, this is for the boundary of this square, but you could also put obstacles inside the domain. And then the equation on phi and the maximization on Q will be slightly different on the boundaries, but it doesn't change too much the ADMM numerical scheme. So let's see an example. Now we start with M0 uniform over a small square in this corner, and we take a cost that attracts people on the other side of the domain. Right? So it's minimum on this little square, so people should be concentrated on this square at the end of the simulation. And now I'm not going to play with the parameters, I'm going to play with the boundary conditions. So first of all, periodic boundary conditions. So what do you expect? So actually, the mass uses periodicity to travel very quickly to the other side of the domain. So it never crosses the domain, actually. And at the end, you have something with a very high value on this side because most of the mass comes from this side, actually. Now, if we put state constraints on the boundary of the domain, then, of course, the mass cannot cross the domain, so it cannot use periodicity, so it has to cross the domain. And then the final mass looks like this, so very concentrated on this side because it comes from here. Now if I put an obstacle in the middle, so you don't see it here because it's encoded in the Hamiltonian, it's not in the domain, but let's say you have some obstacle in the middle, a little square that the mass will have to avoid. So you see it splits into two parts and avoids this obstacle. But the final shape is more or less the same. So, very briefly, it will be much shorter, but I will present a second model, which is actually smoother, at least, so mathematically it's somehow simpler. So I will write the model. You have the same dynamics, so the agents control their speed. Now, the running cost is a non-local function of the density, right? So I use again the notation with brackets because it may depend on M in a non-local way. Actually, it will depend in a non-local way on M. Now, the PDE system is very similar to the previous case, except that since the dependence is non-local, this derivative with respect to M is in a different way, defined in a different way. So here it will be the Gato derivative, assuming it exists. And then we integrate with respect to the density M. So this is the system of PDE you get in general for a general mean field control problem with non-local dependence in the running cost. Of course, there could be also a dependence on M in the final cost. And then here, for the terminal condition, you would also have ut at M and X plus the derivative of ut with respect to M. So you would also have an additional term here. But for simplicity, I take ut depending only on X and not MT. So I will just give two examples for which we are able to show existence of classical solutions. So here we don't need weak solutions. And actually there is a larger class of Hamiltonians for which this works, but for simplicity I take only two examples. So the first one is H1. So both of them have more or less the same form, H1 and H2. However, H2 is subquadratic in P, and both of them depend on some parameter alpha, positive number. And there is some regularity assumption, and also both of them are non-local in M, because M is convoluted with some regularization kernel, rho 1, and also rho 2 in F. Right? But the main part is that there is this regularization with respect to, rho 1. And also, if you look at the denominator, it's a constant. So here 1 plus m to some power. So this will never be 0. Right? You could replace 1 in the denominator by some small constant, but anyway, it will never be 0. So this will never degenerate when the mass is 0. And moreover, I will take a positive diffusion, so positive volatility. So the mass will never be 0, basically. And the way we show existence of classical solution is reminiscent to the techniques of Lazary and Lyons, so by a fixed point argument. So the same techniques that are used in mean field games. And we also have some arguments to show uniqueness of solutions based on some convexity properties. So now I'm going to show some numerical results related to this model. Actually, for simplicity of implementation, I will not take a non-local model, I will take a local model, but still, you notice that the denominator is 1 plus m. So this is never 0, so we don't have the same problem as in the previous setting. And the two constants C1 and C2 are chosen such that the numbers make sense to interpret the congestion model. So here I'm going to represent the evacuation of a room, let's say like this one maybe, where people are, let's say, they are sitting on some rows, and there are some obstacles in the middle, so like tables, and so they have to exit these rows and then go to the exits, which are located in this corner and this corner. Yes? So the cost, the final cost, will be of this form on the right, and you see that it's very high around the back of the room, but at the front of the room it's very cheap. So basically it encourages you to go to the front of the room, and we will add some Neumann conditions on the boundaries and on these obstacles, and we will also add Dirichlet boundary conditions on the doors. Right? So people can exit by these doors. So the mass will vanish at the end of the simulation. Now for the simulations, they are based on Newton's methods that are described in these papers by Ajdu, Caputo-Dolcetta, and others that I'm not going to describe here. And it can be applied to this local Hamiltonian, but also to a non-local Hamiltonian. It doesn't change much. It's just a bit more tedious to implement. So here I took a local Hamiltonian, but it doesn't change too much for the numerical implementation. And on the left, I will present the simulation for the mean field control problem. So I take the PDE of the mean field control problem, and I solve it using Newton method. And on the right, I take the PDE of the mean field game. So without this term in red, that's the derivative of m with respect to h. So let's see what happens. So you see that after a short time, people start going to the side of the room, in both cases. But in the mean field game, on the right, you reach higher values somehow. I think it's even clearer like this, maybe. You can see that, so it's scaled in the same way, 4.5 is the maximum. And you see that on the right, you have higher values than on the left. And somehow this is because people are more selfish, so they try to push and exit as fast as possible, but actually maybe it's not the optimal thing to do. Let's say if you look at a social optimum. And then people exit by the doors here, and at the end, no one is left in the room. And you see that around the end of the simulation, both look very similar, and this is because the time horizon is the same. So everyone should exit at this fixed time horizon. So we don't consider the problem of exiting as fast as possible. Right? The problem is with the fixed time horizon, and just mean field control and mean field game. So to conclude, I've presented two models of mean field control with congestion effect, existence and uniqueness for the PDE systems, and some numerical methods. So some ongoing work. So for the congestion model, I'm looking at the ergodic problem or problems for the different models of congestion, and also what happens for several populations. So for example, two populations. And on the numerical side, there are at least two projects in the SEMRAX related to mean field control. So one is to take this ADMM method and take a positive diffusion. So I've mentioned that for now we take nu is equal to 0 because otherwise we have some trouble to solve some finite difference equation. So we try with nu is equal to 0, nu strictly positive, sorry. And we also work, there is also a project on stochastic methods for some class of mean field control or control of MacKean-Vlasov problems. And then maybe some perspectives. It could be interesting to know the exact relationship between hard and soft congestion. I think so far we don't have a very precise picture of the relationship between these two kinds of model. We could look at boundary conditions in the theoretical framework. So the simulations work for some boundary conditions, but from the theoretical point of view, it's still not very clear. And maybe also, so I've not presented the proof for the existence of weak solution, but the proof is not very straightforward. So we could look for a more direct or a simpler proof of existence of weak solutions. So here are some references, and thank you.
Thank you, Mathieu, for your talk. Do you have any question? Okay, let's thank again Mathieu for your talk.